Okay, so here's what we got today, or kind of for the week. We've got a couple of labs that will help with this whole idea of chemical formulas. Because until you kind of begin to see what's happening, it's kind of tough to figure out the whole concept of writing and balancing chemical formulas. So we got that. Then, so today will be like the first kind of introductory lab into that whole process. Then, Friday will be Africa Day. We'll talk about that. We'll cook breakfast. We'll talk about my time in Africa. You'll see me when I was young and skinny and all that good jazz. So that's kind of the plan for the week. Okay, so let's chit chat about this whole writing and balancing chemical formulas thing. So the whole idea of this is that you're going to represent a couple of things in this process. The main idea is this law of conservation of mass, which says, hey, whatever mass you have to start with is whatever mass you end up with. Okay, that's the whole idea. One of the great conservation laws: conservation of angular momentum, conservation of linear momentum, conservation of energy, conservation of mass. So that's the whole basis of balancing equations. Now, within that, there's a whole bunch of subtleties that play out. Okay. So any chemical reaction, you're going to describe what happens. So on the lab that you're going to do, like for example, one of the things you're going to do is you're going to take some solutions, you're going to mix them together, and you're going to see what makes a precipitate. You're going to decompose hydrogen peroxide. There's any number of things that you can do. And so the first thing you have to figure out is like, okay, what's actually taking place? And then once you figure out that, like, okay, well, what are we going to end up with? So when you look at what your products are going to be, just keep this in mind. Mother Nature is a lazy prima donna. So whatever products that you get is because that's the most stable arrangement and that's the lowest possible energy form. So if you keep that in mind, you go, okay, well, there's only certain rules that can happen. So for example, let's say that I can't find my golf ball. Well, the last place I'm going to look is on the very tip of that flagstick, because that's not where it's going to end up, because Mother Nature is not randomly going to bounce this thing around and have it end up on the end of that flagstick. Now, more than likely, it's probably going to end up in the bottom of that sink on my desk, because that's the lowest energy state. So if you look at these reactions that you're going to do today, you're going to do the decomposition of hydrogen peroxide. For example, your hydrogen peroxide, which is H2O2, okay, and that was one that was missed quite a bit on the writing and naming chemical formula sheet that I just gave back. So hydrogen peroxide is H2O2. And it's fairly unstable, so what happens is that hydrogen peroxide decomposes into water and oxygen gas. So one of the things you're going to do on this sheet is that you're going to draw a couple of diagrams. So you're going to have what we call the atom inventory, and then you're going to have the particle diagram. So the particle diagram is basically saying, hey, do you understand what's going to take place? So your particle diagram is pretty simple. You're going to start off and you go, okay, I got this big chunky molecule of hydrogen peroxide, okay? It's unstable. It's like a bowl full of jelly. So you're going to add a catalyst. Now, if you take AP chemistry, we'll spend a lot of time talking about a catalyst. What a catalyst does is that it starts a reaction, but it's not involved in the reaction. Okay, so what you're going to use as the catalyst is potassium iodide, which is Ki. So a catalyst does not show up in the reaction. So on this very first one that you're going to do, okay, you're going to take hydrogen peroxide, you're going to add 0.5 grams of potassium iodide as a catalyst, and then you're going to take a wood splint, and then you're going to put it into the test tube. So you're going to have this test tube, okay, and you're going to have hydrogen peroxide, and you're going to add this potassium iodide to it. So the potassium iodide is not part of the reaction. It's there, okay, but it's a catalyst. So when you write a catalyst, you technically, and don't worry about this, you'll spend more time. You actually write your catalyst in the line above the arrow. The arrow shows the direction that the reaction is going to go. So when you see Ki up there, that indicates that that's the catalyst. It's there, but it's not involved in the reaction. So it's kind of like you walk down the hall, you run into freshmen. They're there, they're not part of the reaction. They're just there. Okay, same thing is going to be true with potassium iodide. Now, when you do flame tests, there's 3 primary flame tests you can do to indicate if a particular gas is present. One flame test is that you take a burning splint, and this is what you're going to do, and you get it lit, and then you blow it out so it's still glowing a bright orange. And you put that into the test tube. So if oxygen is present, what will happen is that that splint will reignite because the oxygen is reinvigorating that flame, and it will start to glow again. So the test for oxygen is that you take the burning wood splint, you blow it out, you immediately put it in the test tube. If it reignites, oxygen is present. So that's how you test for oxygen. The other test you're going to do is you're going to test for the presence of hydrogen. Hydrogen, that's the one that makes it pop. So with the hydrogen, again, you take a burning wood splint, and this one's actually like burning. You don't blow it out. It's a burning wood splint. And you put it into the test tube. Y'all have done this one before, okay? And if it makes that popping sound, you know that hydrogen is present. So the hydrogen test is different from the oxygen test. So they both involve fire, but it's different. So oxygen won't make a distinct sound, hydrogen will. Okay, so hydrogen, boom, you pop, presence of hydrogen gas. Put a burning wood splint, and you blow it out, and it reignites, boom, oxygen is present. So the third one you can do is the test for carbon dioxide. So carbon dioxide is the opposite. So with carbon dioxide, you take a burning wood splint, and you put it into the test tube. Carbon dioxide actually forms terminal bonds, and it puts the flame out. So hydrogen makes the test tube pop. Oxygen makes the flame reignite. Carbon dioxide makes the flame go out. And oddly enough, which of the 3 do you think we put in fire extinguishers? Carbon dioxide. Okay, there you go, because it puts the flame out. We're not going to spray oxygen onto a burning flame. It's like, oh, that'll be cool. Let's put oxygen on there. That'll make it glow. No. Okay, so this is why when you have, if there's ever a fire, one of the primary ingredients in fire extinguishers is carbon dioxide because it puts the flame out. Okay, so what you're going to do is you can say, okay, on this particle diagram, you're going to go, all right, I got this clumpy stuff of hydrogen peroxide, and then out of that, I'm going to get a water molecule, like such, okay? So I'm going to get that. Why do you think it makes a water molecule instead of like an OH group? Why does it make water? Mother Nature is a lazy prima donna. Guess what the most stable form of hydrogen and oxygen is? Water. Which is why we have oceans full of water and not oceans full of hydrogen peroxide. Okay? Because it's the most stable form. Now, out of that, you're also going to get oxygen. Now, there are certain diatomic molecular chicks, okay? And this is one of the things that you have to begin to know without hesitation. So it's hydrogen, and then it's like an inverted 7 on the periodic table. You start at nitrogen, oxygen, and then it's the halogens. Hydrogen, oxygen, fluorine, all the way down, okay? So when you see those as the elemental form, okay? Not necessarily when they're bound up with anything, but if you see oxygen by itself, or hydrogen by itself, or fluorine by itself, or iodine by itself, those are always 2 that are hooked up. They're not stable by themselves. They're more stable to something else, and that's why it forms like this. So, here's what I'm looking for in the diagram. You're going to have a water molecule, okay? And then you're going to have 2 oxygens hooked up. Okay, so that's what I'm looking for on the particle diagram. Now, the main thing we have to do is that we have to balance this. So I want to make sure everybody's cool with what this looks like when it's balanced. So this is where you start this ping pong game, okay? Everything has to balance out. So start with this. I got 2 hydrogens, that's cool. I got 2 hydrogens over there, I'm done. Okay, the hydrogen is good. I got 2 oxygens over here, but I've got 3 oxygens on that side. So I have too many oxygens on this side. So could I just change this to a 3 and then we're good? Peyton, you shake your head no. Why? Why can't I just make this a 3?
It wouldn't be the same chemical compound if you changed it to a 3.
Fantastic. Hydrogen peroxide is H2O2. So think about this. This is like sacrosanct. Once you get this written, imagine that there's a box around it and you can't change it. Okay? So once you write these, you're done. Okay? You cannot alter them anymore. But this is why you have to be able to write chemical formulas before you write balance reactions. Okay, so what? So I don't have enough oxygens over here, so what can I do? Luke, what can I do? What if I put a 2 in front of here? So I'll put a coefficient of 2 in front of here, right? Now, at this point, how many oxygens do I have on this side?
On this 4?
On the reactant side. I've got 4 oxygens, right? Okay? But now I also have 4.
Hydrogen.
So how can I get 4 hydrogens on the other side?
Put a 2 in front of the 1.
Put a 2 in front of there. Okay, that's cool. Now, at this point, I have 4 hydrogens over here, right? And I have 4 oxygens. Over here, how many hydrogens do I have, Luke?
4.
How many oxygens do I have here?
4.
No, just in here.
Oh, 2.
2. How many do I have over there?
2.
Is everything balanced then?
Yeah.
Okay, so when it asks for the atom inventory, okay, what I want written where it says, and this is going to be the same on all, on the atom inventory, you're going to go, oh, I have 4 oxygens, I have 4 hydrogens. Over here, I have 4 hydrogens, and I have 2 oxygens, and over here I have 2 more oxygens. So the atom inventory, you're just writing down and showing me, oh, these things balance out. So you're going to have a particle diagram, you're going to have an atom inventory, you're going to have the written WE. WE is the written equation. So the written equation, this would you say, oh, hydrogen peroxide turns into water and oxygen gas. Then the balanced chemical equations is just going to be this. Okay? Got the idea. So, on the atomic countdown to balancing equations, does anybody have any questions on this one? Because you got to be able to do this before you do the lab. That's why I gave you this. So let's talk about, say, for example, on number 15. So you've got 3 aluminum hydroxides, okay? So the aluminum is pretty simple. That's just going to be 3 aluminums, right? Now, how many oxygens do you have? 9. Because if you want to think about this, you could write. Some people like to do this. Well, they'll write this as O3H3, like they'll distribute that 3, and then they'll distribute that 3 over the top, and then you got 9 oxygens, and you got 9 hydrogens. Okay. I don't care how you think about it. Some people like to think, oh, I have fundamentally you have aluminum and you have 3 hydroxide groups attached to them. Okay? So some people like a visual approach, well, they'll write it out, and then, oh, I've got 3 of those, so I've got 3 of those groups, so I've got, that's how they can figure it out that way. It makes me no difference. On number 20, just to kind of give you some reference, you should have 96 hydrogens. Okay? On number 14, you should have 9 oxygens. All right? Are we good? Going once, going twice, sold. Okay, yes?
You want to hold 11? How does the 7 work?
Okay. So, here's your periodic table. Okay? So, you start off with hydrogen in the top left corner. And then, it's like this. You go nitrogen, oxygen, fluorine, bromine, iodine. So it's like an inverted 7. like that. Some people, this always annoyed me, but some people they'll remember it like Hoffelbrinkel, something like that. It's in the packet listed that way. It's just annoying. So it's just hydrogen and then that second. There you go. But listen to me. Here's the most common misconception. The only time those are automatically diatomics is if they're by themselves, okay? So for example, you look at this first reaction you're going to do. You have water. Notice that oxygen, when it's water, is just a single oxygen. So I don't want you to look at those and go, oh, every time I write these elements, there's always going to be two of them, okay? There's always going to be two of them when they're by themselves, okay? See the difference between the two. Got it? Good, Brand? Okay, get that handed in. Let me hand out the lab. Stop that hand. Okay, so let me kind of get you started on all of these reactions so you have an idea of what's happening. First one I already talked about, hydrogen peroxide. The other thing that you want to do is you want to list the type of reaction. So in the type of reaction, you can have decomposition. So that's what's going to happen on this first reaction. You can always recognize decomposition reactions because you start with one thing and you break it down into something else, okay? Now, on the second one, you can take a strip of magnesium, hold it in the pair of tongs like I did back there, put it in the flame. It's going to burn very, very brightly. So decomposition, the opposite of that is a synthesis reaction. So in a synthesis reaction, you take different elements or different atoms and you combine them together. So what's going to happen on the synthesis reaction is that, imagine this is the magnesium, okay? So when you have just one thing by itself, it's just magnesium, boom. It's just going to be Mg. Now, what reacts in our atmosphere is oxygen. The nitrogen doesn't react, and that's a cool thing. We'll get into that later. It's a good thing that nitrogen doesn't react like oxygen does, okay? So what's going to happen is the magnesium is going to react with oxygen in the air, and you're going to form magnesium oxide. And I'm abbreviating this in the name of time. Okay? So what's going to happen is the magnesium, here's the chunk of magnesium, here's oxygen, is one of the diatomics. So the magnesium is going to come in, and it's going to hook up with the oxygen, and you're going to form magnesium oxide. Now, this is a situation where you have to be able to write the chemical formula for magnesium oxide. So you've got to look and go, oh, what's the charge on magnesium? Oh, find that on the periodic table. Oh, what's the charge of oxygen? Find that on the periodic table. So let me give you a hint. You're going to get magnesium oxide. This is why you've got to be able to write the formula for magnesium oxide. So do that over a watch glass so that the hot ashes don't fall onto the surface. So again, you're going to have a particle diagram, chunk of magnesium, here's oxygen, you're going to lump them together into magnesium oxide. On number 3, you're going to take a piece of zinc, drop that in hydrochloric acid. So again, with this one, you take zinc, hydrochloric acid. So you're just going to start off with this, zinc, hydrochloric acid. Okay, now, one of the things you're going to do is you're going to do a flame test with burning splint. You're going to drop that in there. Hopefully it pops. Okay, this is pretty much a home run. So you know one of the gases that you're going to get is going to be hydrogen gas. That's the proof for hydrogen gas. Okay, is do you get the popping sound? Now, what's going to happen here is basically the zinc is more reactive than the hydrogen. It comes in and kicks the hydrogen out, so the zinc is going to bond with the chlorine. So this is what's known as a single displacement reaction, because you have the zinc off by itself, the hydrochloric acid is there, the zinc comes along and says, so what's up? Hydrogen basically says, I'm out, you dance with the chlorine. You want to dance with her? She's all yours. Hydrogen says, I'm outie. So you're going to get zinc chloride out of this because the zinc is going to bond with the chlorine. Now again, at this point, you have to be able to write the formula for zinc chloride. Look at the oxidation state of zinc, look at the oxidation state of chlorine. Okay? So you have to be able to write the formula for zinc chloride. Okay? If you can't do that, you're kind of dead in the water. When you get to reaction number 4, you're gonna take a piece of copper, okay, boom, there you go. You're gonna put that into a solution of silver nitrate. So what's gonna happen, and this is gonna be important that you understand what's happening on an atomic level. So you're gonna have a chunk O carbon, and we're gonna write this as silver nitrate, okay, AgNO3. Now, because it's a solution, and this is gonna be important that you begin to get this visual model of what's taking place. When it's a solution, when you draw that particle diagram, so you're gonna have this wire made out of these coppers, okay? And those coppers are all lumped together. That's what makes a copper wire. But your diagram, that's gonna be a silver ion and a nitrate ion. There's a huge difference between a powder of silver nitrate and a solution of silver nitrate. So if it's a powder of silver nitrate, like if you go into the chemical storeroom and you grab a bottle of silver nitrate, kind of a grayish powder, okay, that silver and that nitrate are bound up together. Okay, they're locked up, you can't do anything. This, because it's a solution, you have silver ions and you have nitrate ions, okay? So basically what's going to happen in this reaction is the silver is going to come along to the copper and goes, yo, sup, it's a single displacement reaction. The silver is more reactive than the copper is. So what's going to happen is that the silver is going to take electrons away from the copper is going to bond with the nitrate, and then the copper is going to go into the solution. Now, so with this one, because there's different oxidation states of copper, Cu2 plus is the most common. So when you do reaction number 4, what you're going to get out of this is that you're going to form copper 2 plus, okay? So that's because that's the most stable form of copper. So what's going to happen is that the silver is going to come along, it's going to take electrons from the copper is going to go into the solution, it's going to bond with the nitrate, and then what you will see is actual elemental silver forming on the outside of that copper wire. So what's going to happen is that you have solid silver, because you have solid copper. The silver ion comes along and says, yo, give me your electrons. Copper says, fine, you want them, take them. But the rule is, in a situation like this, once that silver takes its electrons, it forms elemental silver, and it comes out of the solution. The copper, once it gives up its electrons, has to go into the solution, okay? So this is what we call a single displacement reaction. It's also a redox reaction. It's a reduction and an oxidation. So basically what happens, the silver has a stronger pull for the electrons than copper does, and it's like a tug of war. The silver comes along and says, yo, give them up. Copper says, there you go. So it's like a bully taking milk money from a freshman, okay? The copper says here, but then the copper's out and it goes into the solution. Now, when you get to number 5, you're going to have a solution of hydrochloric acid, so you can have HCl, and you're going to react that with sodium hydroxide, okay? Now, these are both solutions, so these are existing as ions. They're existing as hydronium ions, chloride ions, sodium, and hydroxide. So this is a reaction we did on Friday. This is what's known as a double displacement reaction. So basically, the hydrogen is going to come over here. It's going to hook up with the hydroxide. The sodium is going to hook up with the chlorine. So it's like they're going to switch, they're dancing, and they're going to switch partners. So the hydrogen is going to bond with the OH. So when that hydrogen bonds with the OH, what do you think you're going to get as your product? Water. Why? Why don't you get hydrogen peroxide? Be cool. Why do you get water?
Because there's 2 hydrogens and 1
No. Energy.
Most stable.
It's the most stable form. It's the bottom of the energy well. Okay? That's why we get water. If hydrogen peroxide was at the bottom of the energy well, we'd get hydrogen peroxide. Water's at the bottom of the energy well. It's the bottom of the sink. We're going to get water. So you're going to get water and basically salt. So you're going to get salt water out of it. Okay? Now, when you get to reaction 6, okay, you're going to have a solution of sodium chloride. Okay? So oddly enough, you're going to have sodium chloride. This is a solution, which means there are existing as separate sodium ions and separate chloride ions. Then you're going to add to that silver nitrate. Again, this is a solution of silver nitrate. Okay? We write it like this, but in reality, on the atomic level, they are existing as separate ions. Okay? They're bound to the water molecules. So basically what's going to happen is the sodium comes along and it's going to go, yo, nitrate, sup. Okay? So those two are going to hook up, and then the silver is going to hook up with the chloride. Okay? So what you're going to see is, and here's what I want. Like on this particle diagram, I want you to show me, oh, these are sodium ions, and these are chloride ions. And these are silver ions, and these are nitrate ions. So what you're going to get out of this is a precipitate. When something forms a precipitate that goes from separate ions, boom, they're clumping together. Okay? So when you get done, what you'll see is that the silver and the chlorine is what's going to make that precipitate. So when you draw the particle diagram at the end, put that silver and chloride together, because that's what made the precipitate. So they went from being separate ions, whoop, hooked up, now they're a couple. Okay? And it's love, true love, so they're going to hang out together. The nitrate and the silver, or the sodium and the nitrate, those are still existing as ions. So they're still there, and they're attracted to each other, but they're just kind of floating around going, we're just friends. Okay? But the silver and the chlorine, they're going, whoo, hello, sweetheart. Okay, so we've got to get over there, work efficiently. Focus on getting the lab itself done. Okay? Make observations. What's going on? Focus on getting the lab itself done. Okay? Make sure that you are wearing safety glasses because a lot of this stuff is fairly nasty. Okay? So make sure at all times that you are wearing the safety glasses. Let's go. Hup. Okay. So here's what I'm looking for. Let's say, for example, let's take reaction number 4. Okay? So here's what I'm looking for, is that you understand that first off, you reacted copper. Now, don't put Roman numerals after this, okay? Because this is a big, long discussion about redox reactions. Here's the opening salvo. When you have an elemental substance, the oxidation state of any elemental substance is 0, okay? Aluminum, hydrogen, whatever it is, okay? So the oxidation state of anything in its pure form is 0. It's bonding with the other atoms around it, and we know that because it's solid copper. If the copper didn't bond with the other copper atoms, it wouldn't exist as solid copper. So, but what you have is pure copper atoms. So what you did is that you added silver nitrate. So the word equation is going to be copper plus silver nitrate. Now, why don't I have to put a Roman numeral after the silver? Yeah, silver is only 1 plus. Okay, that's why I don't have to put a Roman numeral there. So on an atomic level, if you could shrink that down, here's this copper wire, and you had all of these copper ion or atoms that are hooked up together, and they're bound up. Okay, they don't have an oxidation state. And then what's going to be important is that you realize these are silver ions and these are nitrate ions that are in the water. Okay, now technically, and you'll see this, what you should write at the end of this is the letters AQ in brackets. That stands for aqueous. So when you see AQ at the end of it, that means this is existing in a substance dissolved as water. Sometimes you'll see after the copper, sometimes you'll see a brackets and S to indicate that this is a solid piece of copper. Sometimes you'll see it written with a CR to indicate that it's like the crystalline form of it. Okay? S and CR just basically means that, hey, this is a solid form of this. So when you write this, you're going to say, okay, here's solid copper. I'm going to react that with aqueous silver nitrate. So basically what happens is this. This is called a redox reaction, a reduction and oxidation. Leo says go. So basically what happens on an atomic level, the silver is missing an electron. The silver comes up to the copper and says, hey, can I take an electron? The copper says, fine, take it. I don't care. Now, the electrons are feeling put out at this point. These copper atoms were formed in the deaths of collapsing stars. These copper atoms have been together a long time. Probably buried in a mine somewhere, they've been processed, they've been heated, they've been extruded through this to make this little piece of copper wire. These have been through a lot. And all of a sudden, this silver ion comes along and says, hey, can we take your electrons? And the electrons go, we're out. And the copper is feeling a little put out at this point. It's like, dude, we've been together through a lot. We started in the death of a star. We reformed on this planet Earth. We've been mined. We've been heated. We've been extruded through a machine. We got this piece of copper wire. We've been on the shelf together for years. And some silver ion comes along and you're bailing ship. They go, yep, that's it. We're out. Okay, so it's like drama on an atomic level. So the copper says, fine. You want your electrons? Fine. So then out of this, what you hopefully saw in the microscope is that you saw the silver forming. So the rule is, once the silver takes in the electron, it can't exist as a single ion anymore. It has to become a solid piece of silver. Then, but the copper, once it goes into the slip, once it gives up its electrons, these are going to switch places. This is why this is a single displacement reaction. Sometimes lots referred to as a redox reaction. So redox reaction, single displacement mean the same thing. So out of this, you're going to get silver and copper. Now I need to put the Roman numerals after it because now it's formed an ion. Now I need to say, hey, did I form copper 1? Did I form copper 2? It's going to form copper 2 because that's the lowest possible state. So then you can have copper 2 nitrate. Okay, so there's your word equation. Copper plus silver nitrate is going to yield silver, and that's solid silver. And then the copper nitrate, if you really want to get fancy, you're going to put AQ on the end of that because that's aqueous silver nitrate. So the nitrate isn't involved in the reaction. It's there, but it's what we call, it's just there to watch, okay? It's not part of the reaction. It's just it's an observer, okay? So the nitrate is there, but it's not involved in anything. It's just watching what's taking place. So what I'm looking for on the particle diagram, so I just want you to put, hey, here's this chunk of silver, and then you're going to have some silver ions, and then you're going to have some nitrate ions. Okay, that's going to be important. You realize these are not, that silver nitrate is existing as ions. It's not a chunk of silver. It's a silver ion. And then that's going to form copper 2+. So those are going to be existing as ions. You're going to have nitrate still existing as ions, but then you're going to have a chunk of silver. Okay, so we went from a chunk of silver, a chunk of copper, a silver ion and a nitrate ion, to a copper ion, a nitrate ion, and a chunk of silver. Okay? Now, what I'm looking for with the atom inventory. Okay, so now we got to do the equation. So we're going to have copper plus silver nitrate. And again, if you want to get fancy, what I would begin to recommend that you do is actually like put a space there for the coefficients. Because if you don't, then you have to go back and put in the coefficients, and then it gets really crowded. Okay. So what I would recommend is that you just get in this habit of putting like a dashed line in front of the compounds. Because that way then you don't have to try and squeeze in a coefficient in between. So I'm going to get copper 2 nitrate. Now, how am I going to write copper 2 nitrate? What's going to be the formula for copper 2 nitrate? So I've got copper at 2+, and I've got nitrate at 1-. So how am I going to write copper 2 nitrate? Parentheses with a, okay, then what? And then I've got silver. Okay? So is it balanced? Wish I had $1 for every time I asked that in the class. Is the equation balanced? Peyton,
No,
why?
because there's one more nitrate on the,
So how, fantastic. So how am I gonna get 2 nitrates on the other side?
if you put a 2 in front of the silver nitrate.
So put a coefficient of 2, there, that's cool. But now I have 2 silvers. So how am I gonna get 2 silvers on the other side?
Putting 2 in front of the silver on the other side.
There you go. Now everything is balanced. So then, on the atom inventory, you're gonna come down here and go, okay, I've got 1 copper, I've got 2 silvers, I have 2 nitrates, okay? And then I'm gonna have 1 copper, 2 nitrates, and 2 silvers, okay? That's just forcing you to think through and understand, wow, this thing is balanced. So, there's your particle diagram, okay? There's your balanced chemical equation. There's your word equation. And it is a single displacement reaction. Okay? Got an idea of what I'm looking for. So, when you do the sodium, that reaction number 6, station 6, the sodium chloride and the silver nitrate, again, with that one, here's what I'm looking for. Now that you've seen that reaction, hopefully that makes sense. So, on the particle diagram, you're going to start off with sodium ions, chloride ions, silver ions, and nitrate ions. So everything is existing as ions. The silver comes along and it goes, yo, chloride, let's hook up. So that's that chunky white precipitate that you saw, was that formation of the silver chloride. The sodium and the nitrates are still existing as separate ions. So on an atomic level, what I'm looking for is that over here, you draw that silver chloride as a chunky thing, okay? Because that's what happened. The silver, the chlorine said, yo, let's hook up, okay? So that attraction was very, very strong, and that's why it formed that precipitate. The sodium and the nitrate, they're attracted to each other because of the fact they're oppositely charged, but they're just friends, so they're still floating around in the solution. They're attracted to each other, but just not enough to make that commitment to say, hey, let's form a precipitate, okay? So they like each other, but they're just friends. But the silver and the chlorine, whoa, let's hook up, okay? And that's why that settles out as the precipitate. So do you have an idea of what I'm looking for on all of those? Carter? So does anybody have any specific ones that you want me to discuss? Going once? Twice? Yes, this is due tomorrow. Okay. Going once, twice, 3 times? Yes.
Do you want us to put the S in AQ?
That's up to you.
Okay.
Eventually, you're going to have to do them on the reactions anyway. It actually conveys more information. So the sooner you get used to that idea, the better off you're going to be. So it's not mandatory, but I would recommend it. Because it shows, because once you begin to understand what's happening on a particle level, then it makes it easier to do the reactions. Because otherwise, you're just writing them down and you really don't know what's going on. So I prefer that you do, just because if you don't, I'm not going to count it wrong, but the sooner you begin to get into that habit, the better off you're going to be. Because eventually I am going to really have you do that.
So then what's the solid on number 6?
Huh?
So then what's the solid on number 6?
That silver chloride.
Okay.
Sometimes you'll see it written, because when it forms a precipitate, and later on we'll get into what's known as net ionic equations. If something forms a precipitate, sometimes you'll see it drawn with an arrow beside it that says, oh, that's settled out of the reaction as a precipitate. So you could put a down arrow, or you could put, hey, that's my solid, something like that. Okay? I actually, if you still wanna order something on that clothing merch, I will still, because I'm still waiting to hear back on some stuff. So if you're still thinking about that and you wanna get an order form in, that's cool, if you wanna do that. Even if you wanna see if other members of the family want it, that's cool too. It isn't just limited just to you guys.